In this question, p and q are positive integers with q being greater than p. Statement 1, q cubed minus p cubed is never a multiple of 5. Show by means of a counterexample that statement 1 is not true. Okay, so we just got to find a pair of cubics for which we do get a multiple of 5. Just trying to think. If we think of, I'll just start by writing. You see, I'm coming at these blind. I'm not. I haven't looked up. This is how I would perhaps just off the top of my head start to approach this. We'll start by writing some cube numbers: 1, 8, 27, 64, 125. 200 and it's not that. I can never remember 6 cubed. I don't know why, it just never sticks in my head. 216. 343, isn't it? Yeah, verify that. 343. 8 cubed is 512. Oh, well, of course. I mean, I'm going to get to 10 cubed in a minute, which is 1,000. And 1,000 take away 125 is definitely going to leave me with a multiple of 5. So, yeah, we'll just use those. Easy peasy. Right, okay. So, show by means of a counterexample. So, if Q is the greater one, so if Q equals 10 and P equals 5, then Q cubed minus P cubed is 10 cubed minus 5 cubed, which is 875. 875 is 5 lots of 5 lots of 175, therefore a multiple of 5. Or you could just say it ends with a digit 5, therefore it's a multiple of 5. I think it's pretty clear if that's a multiple of 5 or not, but we're doing a proof, so we kind of want to get into the habit of concluding with some kind of statement. Okay, this one tripped people up. Most people found some cubic numbers that gave you a multiple of 5. Wasn't too bad. Question 2, P and Q are consecutive even integers. Consecutive means one and the next one, or one and the one before it, but two that are next to each other. So some people try to define their even integers as two different things. So they might have said 2n and 2m, for instance. But these are just two integers that are both even. There's nothing about those that tells us it's consecutive. So we haven't proven what they've asked us to prove unless we can find an algebraic notation for two consecutive even integers. Well, we know 2n is an even integer. The next even integer we get when we add 2 onto the one we're at now. So 2n and 2n plus 2 would work. Yeah. Or you could do 2n and 2n minus 2, because you could have the one before it. You could even have 2n plus 2 and 2n plus 4. Those are two even integers that are next to each other. I wouldn't pick that. There's no point in adding these extra complex things in. Either of these two options will do just fine. Again, either of them Algebraically, these both represent consecutive even integers, so it doesn't matter which we choose. One of them will do. So P was greater than, which way around was it? Q was greater than P. Yeah, so Q's got to be the bigger one, and P has got to be the smaller one. So we're going to do 2n plus 2 cubed take away 2n cubed and see what we get. So 2n plus 2 cubed, if we square it, you could use your binomial expansion really. Old habits die hard, I guess, and I tend to find myself just doing it this way. So square it, we'll get 4n squared plus 4n, hang on, plus 8n. Might as well do it all in one hit because I've not made that bracket very big, plus 4. Multiply out by 2n plus 2, so I'm going to get 8n cubed plus 16n squared plus 8n plus 8n squared plus 16n plus 8. Then I'm going to take away the 2n cubed, which is 8n cubed. I can see that that's going to cancel with that, giving me 16n squared plus 8n squared is 24n squared. 8n plus 16n is 24n plus just the 8 there to add on. Okay, we're showing that this is a multiple of 8. That means we need to take 8 out as a factor. I'll just fill in this gap here because the 2n cubed vanished from that line. So just follow my line of reasoning down the page there. Take out my factor of 8. 8 lots of 3n squared plus 3n plus 1. So this is a multiple of 8, algebraically defined. If we've got 8 in front of the bracket, a multiple of 8. So just write that, multiple of 8, or even which is a multiple of 8 as required. And that's the pure done.